things. And this began to raise for us a deeper set of questions about what might be some of the biological and genetic precursors of some of these phenomena. For example, one of the basic questions here is, when human beings have emotions, we show them. Why do we show our emotions? Why do others copy our emotions? This begs a certain set of fundamental evolutionary questions, which we then engage in another set of projects. But before getting to that, we kind of tried to synthesize some of the work that we've done on the 3 degrees of influence. So while we believe that there's been nice work by Duncan Watts looking at, with an email experiment, many of you might know, confirming the kind of 6 degrees of separation argument about human populations. While we might be connected on average to everyone else on the planet by 6 degrees of separation, we think we're only able to influence and are influenced by people up to 3 degrees of separation. So we've done work on obesity, smoking, happiness, loneliness. It's coming out soon. We didn't show you that. Drinking, depression, those papers are forthcoming. We have a nice set of experimental results on cooperation. If I'm nice to James, then he'll be nice to you, stranger to me, and then you'll be nice to her, stranger to both of us. So you can have a kind of pay-it-forward cascade we've shown with some nice experimental work. And other people have done work, for instance, piano teacher referrals tend to go about 3 degrees. The average piano teacher will find their students within 3 degrees removed from them. Or spread of inventor ideas. A typical inventor will cite or be aware of patents by other inventors who are within 3 degrees removed from them, net of the probability that the inventors are working in the same intellectual area. So the awareness, the information awareness, is also governed, it seems like, by this type of property. And we imagine, and we discuss in the book, we have 3 hypotheses about how this might work. One is picking up on the theme that we talked about earlier, this kind of pebble in a pond. There could be like an intrinsic decay, right? As the radius from the impact increases, the energy, the wave height declines, and the energy eventually dissipates due to friction. So one would be just intrinsic decay in the flow of information or other kinds of processes of influence. Another is what we call the network instability idea, and we've been doing some work on this area. Here the argument is like this. If you think about the people who are 1 degree removed, we can think about this like electron shells. So if you think about the people who are 1 degree removed from me, they're very tight. They don't change from moment to moment. And 2 degrees removed from me, they're a little less stable. So my friend to friend, I could lose the tie to that person because my friend dies or moves, or my tie to my friend gets severed, or my friend's tie to his friend gets severed. So the people 2 degrees removed from me aren't the same as much from time to time. Even more so for 3 degrees. The argument is that at 4 degrees of separation, the people that are 4 degrees removed from you today are not the same people as the people that are 4 degrees removed from you in 2 days or in a month or in a year. Because that shell is constantly changing around you. And so here the idea is you don't influence and are not influenced by people 3 degrees removed from you because they're not the same people. And our final argument picks up on some ideas by anthropologist Robin Dunbar, and probably most of you know about Dunbar's number. It's what we call the evolutionary purpose argument. Here again, picking up on some material we're going to talk about in just a moment, human beings evolved and emerged to be in nested network populations of about 150 to 300 people. And here the argument is we're not built to be sensitive to stimuli that have come from more than 3 degrees, nor to influence people that are more than 3 degrees, because 100,000 years ago, there was no one more than 3 degrees removed from us. The mean path length in a population like this might only be about 3 degrees. And so this is speculative, but we have some ideas about it. So this line of work on what might be the causes of 3 degrees of influence, and also on the emotional work that we've done, the work on emotional spread, has gotten us to thinking a little bit about the fundamental biological determinants of network structure. So here's another simple idea. Here's a sodium chloride crystal. You're all familiar with this. Ask yourself this question. All the pictures of networks that I've shown to you so far look nothing like this. They do not look like a regular lattice. But a human population could, in theory, look like this, look like a regular lattice, where every single person is connected to 8 other people, and all those people are connected to 8 other people, and every spot in the crystal is isomorphic to every other spot in the crystal. So everybody looks like everybody else. But that's not the case. Human beings do not, in fact, form or live out their lives in regular lattices. Social networks have a very different and very particular kind of structure. And in fact, the striking patterns of human social networks and their ubiquity and their apparent purpose beg the question of whether we evolved to have them and have particular kinds of social networks and, in fact, have heterogeneity in our topological locations within social networks. So let me walk you through that for just a moment. And here's a typical network. This is actually a network of 105 students at an elite Northeastern university. Imagine now that you could choose to be individual B or individual D. What's the difference between B and D? B up there and D here. Well, B has 4 friends, and D has 6 friends. Okay? And so you can imagine circumstances in which it might be to your advantage or disadvantage to have more or less friends. For example, most people think it's better to have more friends. It makes your health better, it makes your emotional life better, and so forth. But it's also more burdensome to have more friends. You owe more debts, you have to care for all these people. And some of us are rather solitary. We don't like to have many friends, and other of us are gregarious, and we like to have many friends. There's heterogeneity in the population in B and D. Okay, now consider individuals C and D. They both have 6 friends, 6 ties. You can count them here, 1, 2, 3, 4, 5, 6. This picture's in the book. If you talk to C and D, they would each say that they had 6 friends. So from their perspective, their social worlds look the same. But of course, from our bird's eye view now, they occupy very different realities. And this point can be punched home by asking a simple thought experiment. Imagine a deadly pathogen were spreading through the network. Who would you rather be, C or D? D, right? You'd rather be D, of course. And it's obvious to you now, but if you talk to them, they wouldn't know, because C is going to be buffeted on all sides by this deadly pathogen. Now imagine that a valuable piece of information, or a salacious piece of gossip, not about you, was spreading through the network. Now who would you rather be? C, because this person is going to get information from all sides, right? So now we can imagine, we can begin to construct a kernel of an evolutionary argument where there's balanced selection pressures. There are advantages and disadvantages to being in the middle or in the periphery, net of your vertex degree, net of how many ties you have. Okay, let's look at A and B. What's the difference between A and B? What? Mutuality, or transitivity, we would say. So A has 4 friends, and B has 4 friends, but A's friends know each other, and B's friends do not. And here the argument is, if you were going to hunt a mastodon, who would you rather be, A or B? A. Let's get all my buddies together, let's go bring the damn thing down, we're going to kill it. All right? Now, on the other hand, if you want to find a mastodon, who would you rather be? B. Because in A's case, every one of my friends all has the same information. Do you know where the mastodon is? No. Do you know where the mastodon is? Everyone is going to be having access to the same information, just like the Brian Uzi story James told earlier about the shows. You want to have a mix of people who work together and who trust each other with people who bring fresh ideas into the group. So again, we can imagine constructing a situation in which there's balanced selection pressures on having both transitive and non-transitive groups. And in fact, this is what we looked at.
Yeah, so you might wonder, this is an interesting hypothesis, but how would you go about testing something like this? I mean, the claim that we're making is not just that there's differences in where people sit in these networks, but that our biology is in part responsible for these differences. So how would you go about testing this idea, other than getting blood from everybody and carefully working out people's genomes? Well, there's actually an easy trick that's been used by behavior geneticists for a very long time called the twin study. And what this does is it compares how similar identical twins are to how similar fraternal twins are. Identical twins share 100% of their genes. They had exactly the same variant of each one of their 25,000 or so genes. Fraternal twins are just like ordinary siblings. They get 50% of their genes from mom, 50% from dad, and so they share about 50% of their human segregating genes on average. Now, if you buy the assumption that these two different kinds of twins have similar environments in terms of how they act on networks, then what that means is that if the identical twins' network properties are more similar than the fraternal twins' network properties, then the only thing that could be causing that is the fact that they have more similar genes. And in fact, what we can do is we can very carefully work out not just that there's a significant difference between these two groups, but we can estimate how much of the difference in network structure can be attributed to the genes. We call this measure heritability. So the more heritable something is, the more the variation in a specific population can be accounted for by differences in people's genes. And when we applied this to the National Study of Longitudinal Health, this is a study of adolescents all around the country. It's nationally representative. We looked at about 1,000 twins. And when we did this, what we found was that there were 3 network properties in particular that were heritable. Okay, so the first one is in degree. This is just the number of people who name you as a friend. So not a surprise there, right, that popularity is going to be in part genetic. We have different amounts of face symmetry. We know that face symmetry is related to subjective perceptions of beauty, and that beauty is related to how many people are going to call you up for a date, right? And so this is nothing necessarily to shout to the rafters about. Transitivity, though, is also heritable. about the same amount, about